السلام عليكم ورحمة الله وبركاته. طلاب إن شاء الله تكونوا زينين. محاضرتنا لهذا اليوم هو مزيد من الأمثلة حول الفيكتور سبيس. أخذنا بالمحاضرة السابقة تعريف الفيكتور سبيس وأخذنا عليه مثالين، مثال الآر ومثال الآر إن. اليوم ناخذ إن شاء الله مزيد من الأمثلة. مثال example 3 the set of all m times n matrices is denoted R m times n. It forms a vector space with respect to matrix addition and scalar multiplication. This is a vector space because we define scalar matrix addition from R m times n cross R m times n into R times m times n. And also we define scalar multiplication from R cross Rm times n into R times m n. And this is matrix addition. We call this matrix addition and this scalar multiplication. Here scalar from R and here matrices. Here matrices, some matrices in the same should be have to be in the same size. Notice that we cannot mix matrices of different sizes, since we have no natural way of adding them. We cannot adding them because this matrix of different size we cannot add them. So they are not defined. Now we have to prove all since all axioms of vector space are satisfied. A1, A2 until A10, all of them are satisfied. So this is clear is a vector space. This is clear a vector space. This is page number 1. Another example, example 2, example 4, sorry, example 4. Let f of R denote the set of all functions functions with domain with domain R. Let fg belongs to f of R, and suppose C belongs to R. Define addition function addition of functions by, we define addition functions by f plus g of x equal f of x plus g of x for all x belongs to R. And likewise for f belongs to f of R and C belongs to R. Define scalar multiplication of a function by a constant in the in this way. C f of x is equal to C f of x, and this is addition. This is define of addition function, and this is define of scalar multiplication. So we have to define two operation. For all x belongs to R. For all x belongs to R. And also all the scalar addition function defined from f of R cross f of R into f of R, and scalar multiplication defined from R cross f of R into f of R. And this is, in any vector space we have to define two additions, two operations. First operation addition, and second scalar multiplication. We have to define both of them, sum of function and scalar multiplication. On this page number 2. Axioms of vector space. A1, A2 until A10 are satisfied. Are satisfied. This is easily to satisfy. We can satisfy all of them from A1, A2 until A10. Now we take another example. Example 5. Let P2 derivative of polynomial is equal to ax squared plus bx plus c, such that a, b, c belongs to R. The set of all polynomials up to quadratic 2. Quadratic order. من الدرجة الثانية. Also we have to define two operations, sum and scalar multiplication. Define addition and scalar multiplication by the usual operations on polynomial. Polynomials. Notice that if ax squared plus bx plus c and dx squared plus ex plus f belongs to P2. P2, this space we defined previously. This P2. X2, x, and this without x. Here, A, B, C. And we take two vectors in this space, P2. This is first vector, and this is second vector. Then ax squared plus bx plus c plus dx squared plus ex plus f is equal to we sum this with this because this x squared and x squared, so this is equal to a plus dx squared plus, and this with this, b plus ax, also this with this, plus c plus f. This is also belongs to P2. Thus plus defined from P2 cross P2 into P2, also into B2. It's page number 3. Similarly, d ax squared plus bx plus c is equal to dax squared plus dbx plus dc. This is belongs to P2. Thus, scalar multiplication maps R cross P2 into P2. And now we define these two operations. Sum operation and dot scalar multiplication. And now we can satisfy all axioms of vector space. All axioms of vector space A1, A2 until A10 are satisfied. You can check them. Check them. This is homework. Check all axioms A1, A2 in the previous example. All previous examples. Example 3 and example 3. Example 3, example 4, also example 5. This is last one. Check axioms of vector space. This is homework. You can do it. I believe you can do it. Now, take this theorem. Let V be a vector space with zero vector and let C belongs to R. C belongs to R. Number 1, 0 dot x is equal to 0 for all x belongs to V. Number 2, C dot 0 is equal to 0 for all C belongs to R. Number 3, minus 1 dot x is equal to minus x for all x belongs to V. Number 4, if Cx is equal to 0, then C equal to 0 or x equal to 0. This is without proof. This is without a proof. It's page number 3. This is 4. Page number 4. We take now law cancellation. Law cancellation. Lima let A, X, Y be vectors in a vector space v. If x plus a is equal to y plus a, then x is equal to y. We call this cancellation law. Cancellation law. Prove. Suppose x plus a is equal to y plus a. Now, by axioms of vector space A4, there exists minus a such that a plus minus a is equal to 0. Thus, x plus a is equal to y plus a implies x plus a plus minus a is equal to y plus a plus minus a. We add for both sides, here and here, minus a. Now, by A2, we find x plus a plus minus a is equal to y plus a plus minus a. This is by A2, associative. So we move these brackets here, and also these brackets we move here. This is associative, which gives x plus 0 equal to y plus 0. Now by A3, we obtain x plus 0 is equal to x and y plus 0 is equal to y. And so we get x is equal to y. And this is finished proof. This is page number 5. And this is, we call it cancellation law. Now we back to theorem to prove above theorem. page number 4, this theorem. We now prove some of them, not all. Because we need cancellation law to prove this theorem. So we have to take first cancellation law, and then we take and then prove this theorem. So prove theorem. Prove 1. This is 1. 0 dot x is equal to 0 for all x belongs to V. Let x belongs to V by A6 2 dot 0 dot x is equal to by A6. You can't take this. Associated with scalar multiplications 2 dot 0 dot x is equal to 2 dot 0 is equal to 0, and this 0 dot x by by A8 and A6 2 dot 0 dot x is equal to, and this is 2 1 plus 1 dot 0 dot x and we can use distribution law. This is equal to 1 dot 1 dot 0 dot x plus 1 dot, this is 1 dot 0 dot x. And now we can also use here associative to move brackets here. 1 dot 0 dot x plus 1 dot 0 dot x, and this is equal to, and this is here 1, move brackets here and move brackets here, and this is equal to one times 0 is 0 dot x plus 0 dot x. Thus 0 dot x is equal to 0 dot x plus 0 dot x. This is the same, and this is impossible just if 0 dot x equal to 0. And by A3 we find zero plus 0 dot x is equal to 0 dot x plus 0 dot x. Using using cancellation law, we obtain zero equal to 0 dot x. Use cancellation law from here and here. Cancel this with this, we get 0 dot x is equal to 0. Since x was arbitrary, it follows that 0 dot x is equal to 0 for all x belongs to V. And this is page number 6. Okay, so we just prove first one and the other still without to prove. So this finish our lecture. Thank you very much.